Welcome to Tech Lab by Sid. In this video, we are going to discuss about concurrency in computer science. What is concurrency? Concurrency is the ability of a system to manage multiple tasks at the same time, though not necessarily executing them simultaneously. It's a technique where tasks are coordinated in such a way that they seem to run in parallel depending on the system's resources. For instance, even though a single-core CPU can't truly execute tasks at the same time, the operating system schedules these tasks efficiently, making them appear to run simultaneously. This is key to ensuring systems remain responsive, efficient, and scalable. How concurrency improves efficiency? The real power of concurrency lies in its ability to allow multiple tasks to make progress at the same time. While tasks on a single-core CPU are not executed at the exact same moment, the operating system manages them in quick succession, giving the illusion of parallel execution. This makes the system feel much more responsive and able to handle more than one task efficiently. Why concurrency matters? Without concurrency, systems would need to handle one task at a time, which could create significant delays and inefficiencies, especially in multitasking environments or systems that need to process multiple requests. For example, imagine a server trying to handle thousands of requests at once. Without concurrency, each request would need to be processed sequentially, making the system slow and unresponsive. By breaking tasks into smaller units and executing them in parallel or interleaved, concurrency allows the system to process more requests at once, keeping everything running smoothly and efficiently. Concurrency in action. To understand how concurrency works, imagine you are using your smartphone or computer. You open a new browser tab to watch a video, and at the same time, a file is downloading in the background. Despite your device possibly having just a single processor, you can still multitask without any noticeable lag. This is because the operating system quickly switches between tasks, making it seem like both the video and the download are happening simultaneously. How it works? In reality, these tasks don't run at the exact same time. Instead, they are broken down into small bursts of activity, with the CPU switching back and forth between them. Each task gets a tiny slice of time, so while the tasks aren't running together, they appear to be, thanks to the speed of switching. This is how a single-core system can manage multiple tasks efficiently, even though it can't truly execute them at the same moment. Time slicing and parallel execution. The process that makes this possible is called time slicing. In a single-core system, time slicing divides the CPU time into tiny chunks, rapidly switching between tasks to give the illusion of simultaneous execution. On multi-core systems, things get even more powerful. Tasks can be assigned to different cores, allowing the system to execute multiple tasks at once in true parallel, boosting both speed and efficiency. Whether on a single-core or multi-core device, concurrency allows you to juggle tasks effortlessly, keeping everything running smoothly without a hitch. Concurrency in multitasking systems. In modern operating systems, concurrency is the foundation of multitasking, which enables a system to handle multiple tasks at once. The operating system plays a crucial role in managing how tasks are scheduled and executed, ensuring that each task progresses without interfering with the others. This allows users to seamlessly switch between activities like browsing, checking emails, and running applications, all at the same time. Single-core processors and task switching. On a single-core processor, only one task can run at any given moment. However, the operating system makes it appear as if multiple tasks are happening simultaneously by rapidly switching between them. This process happens so quickly that users don't notice the brief interruptions, allowing for smooth multitasking despite the hardware's limitations. It's a clever way to maximize the use of the processor's power, giving the illusion of concurrent execution. Multi-core processors and true parallelism. In systems with multiple cores, true parallelism comes into play. Each core can run a different task simultaneously, allowing the system to handle more processes in less time. This results in a significant boost to overall performance. However, concurrency is still essential here, as the operating system must efficiently schedule and manage tasks between the different cores to ensure that everything runs smoothly. Another critical aspect of multitasking is resource allocation. The operating system ensures that each task gets a fair share of resources like CPU time, memory, and input-output devices. This careful management helps maintain system stability and performance, preventing any one task from monopolizing resources and ensuring that all processes can run efficiently without affecting each other. Through effective resource allocation and task scheduling, multitasking systems deliver a smooth, responsive experience, even when managing multiple complex tasks at the same time. Concurrency versus parallelism. Concurrency and parallelism are often used interchangeably, but they're not the same. Concurrency is about managing multiple tasks in such a way that they appear to run simultaneously. This doesn't mean the tasks are executed at the exact same time, but rather that they are coordinated in a way that allows them to progress without blocking one another. It can involve interleaving tasks, where the system switches between them rapidly, or executing them in parallel when possible, but the focus is on how tasks are structured and managed. Parallelism and true simultaneous execution. Parallelism, however, refers specifically to executing tasks at the same time using multiple processors or cores. It's essentially a subset of concurrency that takes advantage of the hardware's ability to perform tasks simultaneously, as opposed to just appearing to do so. In systems with multiple cores, tasks can actually be executed concurrently on different processors, significantly speeding up processing time and improving performance. The key difference lies in how tasks are handled. Concurrency is about organizing tasks so they don't block one another and can make progress independently, while parallelism is about executing tasks simultaneously, leveraging multiple processors or cores. Concurrency ensures that tasks flow smoothly, even on a single-core system, while parallelism enables real-time execution across multiple cores for faster results. Real-world analogy. To make it easier to understand, think of concurrency as a chef in a kitchen cooking multiple dishes. The chef switches between tasks, like chopping vegetables and stirring a pot, ensuring everything progresses smoothly without blocking each other. Parallelism, on the other hand, is like having several chefs in the kitchen, each cooking a dish at the same time. Both methods aim for efficiency, but concurrency focuses on task management, while parallelism is all about simultaneous execution. How concurrency works. Concurrency is made possible through several key techniques that manage how tasks are scheduled, executed, and synchronized. One of the fundamental methods is time sharing, where the CPU allocates small, fixed amounts of time, called time slices, to each task. Each task gets a brief period to use the CPU before the system switches to the next task. This process ensures that multiple tasks can make progress without having to wait for one another, giving the illusion of simultaneous execution even on a single-core processor. To manage this task switching, the operating system uses context switching. When the system moves from one task to another, it saves the current state of the task, such as its register values and program counter, and loads the state of the next task. This allows each task to pick up where it left off, ensuring that no data is lost and that tasks can continue as if they were running uninterrupted. Context switching happens quickly and efficiently, but it does introduce some overhead as the system needs to save and restore the task states each time it switches. When multiple tasks share resources, like memory or files, it's critical that they don't interfere with each other. This is where synchronization mechanisms come in. These tools, such as locks, semaphores, and mutexes, ensure that only one task can access a resource at a time, preventing conflicts and data corruption. Without proper synchronization, tasks might overwrite each other's work or lead to unpredictable results, so these mechanisms are essential for maintaining system integrity. The operating system also relies on task scheduling to manage the execution of tasks. The task scheduler decides the order in which tasks should run and for how long, using scheduling algorithms like round-robin or priority-based methods. These algorithms ensure that resources are used efficiently, with high-priority tasks getting the attention they need while also ensuring fairness among all tasks. Through effective scheduling, time-sharing, and synchronization, the operating system makes sure that concurrency works seamlessly, enabling multiple tasks to progress without interference. Concurrency is widely used in many real-world systems to improve efficiency and responsiveness. One common example is web servers. These servers must handle numerous user requests at the same time. Instead of waiting for one request to finish before starting another, a web server processes multiple requests concurrently. It can serve web pages, process data, and manage connections all at once, ensuring that users experience quick and seamless interactions even during high traffic. Another critical area where concurrency plays a vital role is in database management. Databases allow multiple users to perform read and write operations simultaneously on the same data without causing inconsistencies or data corruption. This is achieved through transaction management, which ensures that operations are completed in a way that maintains data integrity. The ACID properties, that is, atomicity, consistency, isolation, durability, are used to make sure that even if multiple transactions are happening at once, the database remains accurate and reliable. In operating systems, concurrency is used to manage processes, handle interrupts, and interact with peripherals like printers and disk drives. A modern operating system must juggle many tasks at once, such as keeping the system responsive to user input while also running background processes. This is made possible by scheduling tasks concurrently, ensuring that all system functions are performed smoothly and without interruption. In the world of gaming, concurrency is used to manage the actions of multiple players, artificial intelligence behaviors, and updates to the game state in real time. In multiplayer games, the system handles input from all players concurrently while rendering the game environment and updating the state of the game world. This ensures that all players see a synchronized experience, with minimal lag and smooth transitions between different in-game actions. In each of these examples, concurrency helps improve efficiency, responsiveness, and scalability, allowing systems to handle multiple tasks simultaneously without delays or conflicts. Whether it's a web server, a database, an operating system, or a game, concurrency enables these systems to run smoothly under heavy loads, providing better user experiences across the board. While concurrency offers significant benefits, it also presents several challenges that need careful management to avoid system errors and inefficiencies. one of the most common issues is race conditions. A race condition occurs when two or more tasks access shared resources simultaneously, which can lead to inconsistent or incorrect behavior. For example, imagine two threads modifying a shared bank account balance at the same time. Without proper management, this could result in an incorrect final balance, as both threads might read and write to the balance in an unpredictable order, leading to errors. Another major challenge is deadlocks. A deadlock happens when two or more tasks are stuck, each waiting for the other to release resources. For instance, task A might hold resource 1 and be waiting for resource 2, while task B holds resource 2 and is waiting for resource 1. As a result, neither task can proceed, causing the system to freeze. This kind of situation can bring an entire system to a standstill, as no task can make progress until the deadlock is resolved. Starvation is another problem that arises in concurrent systems. It happens when a task is perpetually denied access to resources because other tasks are constantly given priority. For example, in a task scheduling system, if a low-priority task is always preempted by higher-priority tasks, it may never get the chance to execute, leading to poor performance and system inefficiency. Lastly, synchronization is one of the most significant challenges in concurrent systems. When multiple tasks share resources like memory or files, it's crucial to ensure they don't interfere with each other. Without proper synchronization, tasks may conflict, leading to data corruption, inconsistencies, or even system crashes. Mechanisms like locks, semaphores, and mutexes are used to coordinate access to shared resources and prevent these issues, but they must be managed carefully to avoid introducing performance bottlenecks or deadlocks. To sum up, while concurrency can greatly enhance system performance and responsiveness, it comes with complexities that require careful planning and robust solutions to ensure that tasks work together smoothly without conflicts. Concurrency in programming. In programming, concurrency is achieved through several techniques that enable a program to perform multiple tasks at the same time, improving efficiency and responsiveness. One fundamental concept is threads. A thread is the smallest unit of execution within a program. By using multiple threads, a program can handle different tasks concurrently. For example, one thread can handle user input, another can fetch data from the network, and yet another can process calculations. This allows the program to be more responsive, as it doesn't have to wait for one task to finish before starting another. Another key method for managing concurrency is asynchronous programming. This approach allows tasks to run independently, without blocking the main flow of the program. It's especially useful for IO-bound tasks, like network requests or file operations, where the program would otherwise have to wait idly for the task to complete. In asynchronous programming, the program can continue doing other work while waiting for the task to finish. For example, in languages like JavaScript, you can use async or await to manage concurrency, allowing functions to run asynchronously without blocking the program. Concurrency libraries and frameworks. To make implementing concurrency easier, many programming languages offer built-in libraries and frameworks. For instance, Java provides the java.util.concurrent package, which includes tools for working with threads, thread pools, and synchronization. Similarly, Python offers the threading module for multithreading and the Asyncio module for asynchronous programming. These libraries and frameworks help developers manage the complexity of concurrency by providing high-level abstractions for working with multiple tasks, reducing the potential for errors and simplifying the development process. Overall, Concurrency in programming allows tasks to be performed concurrently within a program, enhancing its efficiency and responsiveness. By using threads, asynchronous programming, and specialized libraries, developers can effectively manage multiple operations without performance bottlenecks. In summary, concurrency plays a vital role in modern computing, enabling systems to handle multiple tasks simultaneously and efficiently. It is essential for creating responsive and scalable applications that can perform many operations at once without sacrificing performance. By allowing tasks to run concurrently, systems can make better use of available resources, such as processors, and can deliver faster, more reliable performance. However, concurrency also introduces challenges, including race conditions, deadlocks, and the need for synchronization between tasks. These challenges can make it more difficult to ensure that tasks are executed in the correct order and without errors. Despite these difficulties, mastering concurrency is crucial for building high-performance systems and applications that meet the demands of today's complex computing environments. Thanks for watching the video. Be sure to explore our channel for more content like this.